This is the last lesson of Unit 8 for geometry. We're going to be talking about vectors today, which is potentially a brand new concept for you. It's very possible you've never seen a vector before in your life, other than in that one scene in Despicable Me 1 where the character vector describes a vector perfectly. It's a quantity in math represented by an arrow with direction and magnitude. Oh, yeah. If you've seen Despicable Me, you get what I'm saying. Maybe. If not, then, it's fine. Go look it up. So, a vector, what is it? It is a two-part quantity. Vectors are two-part quantities. They are not scalars. So scalars are the types of numbers that we have used in the past. And I like to describe a scalar as just a number, right? Just a number. So it doesn't have two parts on a scalar. So it's just a 5 or 6 or a negative 3,482 or a 1/2 or a 0.84 or an I or, whatever else, right? So it's just a number, right? A vector has two parts to it. It has both a magnitude. Now, another name for magnitude is the size. Oops. So the size. Direction is direction. Now, direction, we're going to kind of dive into this when we look at some specifics here in a minute. But direction is usually in degrees, right? And it's degrees from the positive x-axis. We'll show you that when we talk about standard form, put it in a picture and all that kind of stuff. Take some notes on it. Let's hit the next thing. So if we are adding vectors, now we're going to show, I'm going to show you how to do this algebraically here in a minute, which is going to be the easiest, bestest way to do it. But adding vectors, a vector, these are two representations of vectors. So there's a couple of different things we want to look at. First of all is they look like a ray and they're not a ray. Because they actually stop. This yellow vector here goes from this place to this place, and it stops there, right? So it goes from the beginning to the end, which is confusing. Now, we know it's a vector because it's labeled this way. And this, I'm going to make this a little bit bigger, kind of blow this up a little bit. Oops, wrong direction. Bigger, I say. So if we have vector A, we notate vectors kind of like, so if this was ray A, we would do a full arrow like that. So what I just drew, and maybe we should do that, just then leave that in our notes. This would be, let me make it a little smaller so I can actually fit it. This would be ray A, right? Right? So rays, remember, start at one point and continue on forever. But a vector has a beginning and an ending point, but it has a direction. And we notate that direction with the arrow. And the difference on how we label a vector is, if we were to do this one, you can see it here, but I'm going to blow it up a little bit bigger. So let me keep that same color. So what we do is we just do a little half an arrow like that. So a little half an arrow represents a vector. So we would call this vector A in this context. So this right here would be vector A. And I made something that looks like an R. Vector. Right? So there's two different ways to think about vector addition. In my opinion, my strong opinion, the triangle method is the better method to think about it, because it kind of starts it all in standard position. I keep mentioning that, and we're gonna hit what standard position is in a second. The parallelogram does not. So what we're gonna do in order to show this is I'm gonna redraw these same vectors down here. So I'm gonna copy this into this space, and then I'm going to copy it, into this space as well. And this one I'm going to put over here. So in the triangle method, I'm going to talk about the triangle method first because I think it makes more sense. Let me grab this one as well. In the triangle method, you take one of the vectors and you put it at the origin. So we could have the origin drawn. We could have the origin drawn right here, right? So you put one of the vectors at the origin. The origin is 0, 0, right? And then you take the other vector and you put it end to end with it. I'm actually only going to copy some of that, but that'll be fine. Take this over here and take this one over there. And then let's erase this little doomy flotchy that we copied. But and then on the triangle method, we take the other vector and we move it to where his tail goes to this other vector's tip. So you line it up tip to tail, right? And so what I mean is he goes like that. So the sum vector using the triangle method, and this is why it would be called the triangle method, the sum would be this vector right here. This one is vector, there we go, vector A plus B right there. This one is vector A plus vector B. Okay. So that is the way that I prefer to look at it and think about it. And I think it makes the most sense and it's the easiest to kind of draw. You could call the triangle method, you could call it a better descriptor might be the tip to tail method. Tip to tail method. Right? So what about the parallelogram method? So I'm going to just pause and rearrange this and show you what it is. That's going to probably be the easiest and most efficient way. We're just going to boop it in. Okay, and we're back. So you can see what we did here. Let me go ahead and deselect. It's going to be easier to see what happening. I will select that again in a minute because I wanted to show you that using either method, you end up with the same vector. So the parallelogram method, you have to you still do tip to tail, but you redraw the other one and you end up with a parallelogram. And so you kind of almost do the same thing as the other one, and you end up with the same A plus B vector on this method as well. You can see now a little bit more why I don't really like the parallelogram method, because it kind of makes you do more work. So if I take this and move it over here and put one on top of the other, you can see that using either method, we end up with the same vector, allowing for, margin of error for, my if I drew it a little bit off or whatever else, but it's the same vector either way. Right? So those are graphically what adding vectors looks like. Let's keep on trucking. Here we go. So I've said several times standard position. So standard position is a vector drawn where its tail is at the origin and then it comes out from there. And there are two sort of ways of describing vectors. One is your standard magnitude. Now you notice this little, I went ahead and threw this in as kind of a freebie here. How about we use the right buttons? This is the Greek letter theta, and it is very often used to represent angles in trig and other maths as well, which we may have talked about, I feel like, in geometry. I don't know, maybe a long time ago, maybe not, I don't know. So we often use that, and we know the degree symbol, and then D for distance. So this is in green would be kind of the normal way to describe a vector. If you're in a physics class or something, you're probably going to want vectors to end up in this form, but it can be helpful often if we're wanting to sort of manipulate vectors to break them down into their component form. So this would be the component form. You notice it kind of looks like, excuse me, it kind of looks like an ordered pair, but instead of having parentheses, we've got these sort of triangle brackets, right? And so that is the main difference between the way we write this. And the X is, of course, the X part, and the Y is, of course, the Y part. All right, each one of these is kind of a vector in its own right. Their directions would just be at 0 degrees or at 90 degrees, which is also worth noting in this, before we kind of dive into the rest of this lesson, that in case you don't know the way that we mark angles on a coordinate grid, it might be worth noting that this is 0 degrees, and then all the way up here obviously would be 90 degrees, and then all the way around would be 180 degrees, and then 270, and then 360. You could keep on going and do 360 plus 90 and get 450. And you could keep on, as you spin around in this circle, we can keep on going, and which will be almost certainly something that you see in pre-cal or trigonometry or something like that, right? Okay, so that's how that works. You probably knew that already, but in case you didn't, there you go, because that's going to come into play in some examples in a minute. So whenever we write a vector in component form, it's always referencing it based on standard position. So that's starting at the origin and the angle going around from the positive x-axis and around counterclockwise after that. And so that's really important. When we have a vector that's listed in component form, it's reference based on the origin, right? Because we can move vectors around in space. We could have this green vector pop up over here and be the same vector, just in a different position, right? So let's continue what we're doing. What is that? What is happening? Why does it keep adding layers? I don't know what's going on. You can go away, you can come back, and you can come back. All right, let's do an actual example. So we have a vector CD that's drawn here. It is not in standard position, which is going to be important when it says to write the component form, because you might be tempted to be like, okay, the component form is 4, 1, but you would be wrong. Right? This would be wrong, because in order to write the component form, what I just said is muy importante, that it has to be in standard form. So this, starting out, this guy, we need to figure out if we moved this to standard form, what would we do? So we have to move that tail up 1. Now we'd have to move up 1, but we wouldn't have to move to the left or the right any, right? Because it's already on that y-axis, so that part is correct, but the x part isn't correct. So in order to write the component form of this vector, the x part would be the same as what it is. So the x part would still be 4, but the y part we'd have to shift up 1, so it would be 1 plus 1, right? Which would give us a component form of 4, 0. Right? That doesn't sound right. What's incorrect there? Oh, because 1 plus 1 isn't 0. I got too many things in my brain today. How about 1 plus 1 is 2? I'm recording this on a Wednesday, and they are my worst days for like everything. I have way too much that goes on Wednesdays. So anyway, there we are. Okay, let's move on to the next example. Right. So find the magnitude and direction of vector v, -4, -5. So this is the opposite, right? So we're given the component form, and we want to turn the component form back into back into its magnitude and direction form, right? And so this right here is going to illustrate why this lesson is where it is in the units. Because this is going to illustrate why we need trig for this thing, because that's what we're going to need in order to solve this. So -1, 2, 3, 4, -1, 2, 3, 4, 5. So it is sitting right here. So the vector looks like this, right? So we need to find the individual components. Now, this is where our trigonometry is going to come in. Okay, so we need to find this distance all the way around there to find the angle. So we need to find that angle. And then we also need to find this distance d. Right? So what we need in order to find the distance d, the magnitude part, we need to, excuse me, we need to use the Pythagorean theorem or the distance formula, right? Because it's the same thing, really, right? What is this distance right here? This distance is -5. Well, it's a distance of 5, right? It has a distance of 5 its vector form is -5. The negative would be the direction in this case. And this has a distance of 4. So in order to find this guy, we could use the Pythagorean theorem to find the magnitude. Pythagorean theorem. So let's do it. So 4 squared plus 5 squared equals the distance squared. 4 squared is 16, plus 5 squared is 25. D squared is just D squared, right? 16 plus 25 is 31. 41. Let me check my notes. Checks notes. Make sure that we're on the right path and we're doing good things. Yep, we're doing good things. D squared. Now to get rid of that squared, of course, we're going to take the square root. The square root of both sides. Square and square root cancel. Now again, for the 5,000th time at this point, when we take the square root of both sides, we actually end up with plus or minus. Plus or minus, but we're going to throw out the -1, the minus part, because we're talking about distance in this case, right? So it is the square root of 41, which is approximately equal to, oh, my calculator's closed. Let me pull it back up. Give me a second. All right, so square root of 41 is approximately equal to 6.4. So the magnitude is approximately 6.4. The magnitude is approximately 6.4. Now we need to find this angle. So this one is a little bit tricksy, right? So let me go here and let me make this a little bit bigger. Look, mommy, I did it. Right? So it's a little bit tricksy because we want this in standard position, which means we want just exactly what I labeled, right? So we want this full distance around here, but the triangle's over there. So we need to start by finding this other angle. So let's start by finding this angle. And then how could we get the whole one? Well, we'd add this little one plus 180, right? So to find this little one, we're going to use trigonometry. So this theta 2, we'll use alpha, this alpha angle, right? In order to find alpha, we've got the right angles right there. So we've got the opposite and adjacent. So that's tangent. We're looking for the angle. So we need the inverse tangent. So the inverse tangent, tangent with a -1, inverse tangent of opposite. So 5/4 equals, oh, thank you. Time to go do stuff with sourdough bread. I'll do it here in a second. Is equal to alpha, and then we're going to pump it into the calculator. So the inverse or arctangent of 5 divided by 4, we in degrees? Yes, we are. Enter, is about 51 degrees. So this alpha measure, this one right there, is about 51 degrees. So how would we find this full theta right there? Well, we would take and do 51 plus 180, right? So that would be 231. So it has a magnitude. Let me see, does our book use a method? There are different ways to notate this. I don't think it does. I think it just says it in words. Let me look. Yeah, it does. There are ways to notate this, but we're going to go simply with describing it. Magnitude of about 6.4 and a direction of 231 degrees. Great. We've just got a couple more things, and they're pretty short. So let's finish this out. Right. Vector operation. So this is really, really easy stuff. So if these are vectors and k is a scalar, then the following things are true. Vector addition. If we have two vectors and we're adding them, all we do is add up their components. Vector subtraction, we just subtract the components. The order would matter on subtraction, right? That's important. And again, we did this graphically as well, right? All right, so it's got that tip to tail method where we stack them up and it'll give this thing. So this is the algebra way to find that, which is a lot easier than trying to manipulate and cut things out and draw them just perfect and redraw and all that kind of stuff. And so, algebra's handy. All right, scalar multiplication is also really simple. If we have a scalar times a vector, we multiply those two things. It's worth noting, this is just a freebie. If you take a scalar and you multiply times a vector, it only changes the size. It only makes it bigger. It doesn't change the angle. So that's a free bit of knowledge for your brain. So let's move on and do the next thing. So for each of the following, I forgot to write down the rest of the words of this problem. So for each of the following, vector R is this, vector S is that, vector T is that. Find for dramatic effect. Anyway, yeah, so let's do it. Let's jump in and do it. So vector R plus vector T. So R plus T. Let's start doing some color coding. R plus T. Great. So we just add up those components. Easy peasy lemon squeezy. So this is going to be R, so 3 plus T, which is 1. So the first part's together, and then the R's Y part, so 4 plus -2. Don't forget all your positive negative rules, all those things, right? So this is easy peasy. 3 plus 1 is 4. 4 plus -2 is 2. So this is 4, 2. Great. SR. So same idea. I think I'm going to abandon the color coding for the sake of efficiency. So S minus R. So S, so 5 minus the R part. So minus 3. Right? Don't really need the parentheses there. Just good habit to be in. So S, so -1 minus R, which the Y part of R is 4. So 5 minus 3 is 2. -1 minus 4 is -5. Cooking. Doing just fine. So this one is a little bit more complicated. So let's do the 2t first. So 2 times vector t equals 2 times 1, that x part of t, and 2 times -2. Breaking this up into steps to make it easier and make sure we don't make mistakes and, all of those great things. So 2 times 1 is 2. 2 times -2 is -4. So now for the last bit, we're going to take this and subtract S. So we're going to do, that's going to end up being this guy, 2t. So 2 minus S. So the first part of S is 5, the x part. And -1, the 2t part, minus -1. See, it's a good habit to just be in, because now we see here we've got to make sure we ka-chink those. Don't make those small mistakes. Don't miss the easy ones, guys. That's really important. Just take the half a second to put parentheses on stuff, and you'll be amazed at what a difference that kind of stuff will make, because it's easy to make small mistakes if you're not careful, if you're going too fast, and all of those things. You guys know it. You've seen me do it. All of that stuff. It's easy to make mistakes if you're tired, if you're going too fast, all those things. So do the things that make it helpful not to miss the easy stuff. That's it for this lesson, this unit, all the things. We'll go back to a little bit middle schooly kind of stuff in the next chapter. We'll see you there. Hasta luego. Bye-bye.